Yeah, let me first talk about, let's see, yesterday you guys took your iReady assessment. I think there were some questions about, when can you finish it? Can you work on it this weekend if you haven't finished it yet? I think so. I just emailed Mr. Fullove uh, just to ask him if is there a deadline or what is a deadline for iReady? Can students work on it this weekend, or is it has to be done by today? So I will get back to you through Remind. So I'll send out a note about that for those of you who didn't finish it and want to know whether you can finish it or when you have to finish it by. Let's look at, I want to point draw your attention to the website. So my website that you've been pulling your notes from. So under the general channel, oops, let me share my screen. Okay, so Mr. Fullove just replied saying that he thinks students can work on it this weekend, but he would prefer that students finish it by tonight. So there's the answer. Yeah, I'll send out a reminder this afternoon to let students know. Try to finish it by tonight if possible, but weekend is a possibility, just not preferred. Okay, so if you go to class website, on the main page, there is the class calendar. I'm updating this calendar on a weekly basis, so I've updated it for next week already for week 3. And right below it is a draft calendar, which is subject to change, but it is, if you want to kind of get a picture as to what we're maybe aiming to do for the rest of the semester. Okay. So as a preview for next week, today we're going to be covering limits, infinite limits. So basically the idea is we know by looking at a graph whether the limit, whether the subcategory for a vertical asymptote is infinity or negative infinity after does not exist. Where after we confirm that there's a vertical asymptote, we know limit doesn't exist. But we can look at the arrows to see whether they're going up or they're going down or they're not consistent. And we could do subcategories or we can subcategorize them. But it's easy to do with a graph, but how do we do it without a graph? How can we still make some conclusions about the behavior of the arrows around the asymptotes just by using the algebraic expression? So that's our goal for today, to identify the directions of those arrows without the use of a graph. So on Monday, we're going to look at limits approaching infinity. So basically horizontal asymptotes and limit as x approaches infinity, using the concept of horizontal asymptotes to determine the limit as the graph heads off the off of the displayed region. Tuesday through Thursday, we're going to be doing review for our test. Our test will be on Friday. And on Tuesday, I want us to do a test run of that process that you'll be taking when you're doing the test. So right now, the overview is that you'll be finding your test under the assignment tab, and that test will become available to you 10 minutes before class starts. And then in that 10 minutes, you can get yourself ready. You can print out the test, and then you can start the test early if you like. And you have to decide, how you want to be taking that test. Do you want to be printing it out and working on paper, or do you want to be pulling it into OneNote and working it on OneNote? So on Tuesday, I'm just going to be doing a practice. I'll probably just put like one problem on it and just have you guys try whichever method you want to try. But I think what right now I'm thinking is that however way you do it, either OneNote or you do it on paper. If it's on paper, you can take a picture of it, convert it to PDF file, and then put that PDF file into a Word document so that if you submit something in a Word document, within a Word document, it allows me to write on your test digitally, and I'm able to grade without having to print anything out, and I'm able to share or return your test back to you with feedback, so you know what you missed and things like that. It makes it easier for us to, or for teachers to be able to efficiently grade the test. So that is what we're going to be trying to practice next Tuesday. And then you have until 10 minutes after the bell rings to turn in your test. So you have 10 minutes before and 10 minutes after to do the preparation of pulling the test or submitting the test. Looking at about 7 to 9 questions, 7 to 9 free response questions, no multiple choice. And we're going to spend 3 days just going through various reviews, and so that you have a good feel for what to expect on Friday. Okay, any questions right now for next week? Mr. Jones is going to he's giving a test today for his BC classes. So I think through that, we'll be able to, I'll be able to get some feedback from him about what worked and what doesn't work. And so I'll use that information to create a kind of a directions that we can follow for Tuesday for our test run, so that we can be comfortable with the process for Friday. All right. Let's go to our notes. I want to start off by recapping what we did yesterday. I don't know if we finished example 2 all the way, so let me show the key and let's walk through it. And see if you guys have any questions. So yesterday, we talked, our main focus was IVT, intermediate value theorem. The big idea with IVT is we just want to know, can we guarantee that the graph is going to cross a y value of the target, whatever they tell you. In example 2, it was 6. Can we guarantee the graph is going to cross through and touch a y value of 6 between the 2 endpoints? So we have a couple of procedures that we have to follow. First, we have to establish that our function is continuous. We don't have a visual picture of the graph. We're relying on just information about the function and the endpoints to help us visualize what's happening. So we always, if there's any discontinuity, it's going to be located in the denominator of our function. So we can set our denominator equal to 0 to look for holes or asymptotes. In this case, this discontinuity is a vertical asymptote. And vertical asymptotes are okay as long as it doesn't affect our interval. So as long as it's outside the interval and we protect our interval, that's all we care about. Our interval is protected. There's nothing that's going to cause any issues between 5/2 and 4, because the only issue that we see is at 1, and 1 is safely outside the interval. So our first condition is good to go, continuous on the closed interval. The next step was we want to know, is this an intermediate value? Is this going to fall nicely somewhere between the y values of my endpoints? So we want to make sure that we don't compare the x values with y values, right? Because then we're not matching information that are the same. So we need to plug 5/2 into the function in for x. We need to plug 4 into in for x for the function, and then we're going to use our calculator to gather the results of our the approximated result of our value. So one endpoint sits at a y value of 5.8. The other endpoint sits at a y value of 6.7. We know the graph is going to be connected between those 2 points. So if we go from 5.8 to 6.7, the graph has to cross 6 somewhere between. So because we have numbers on either side of 6, we can say by IBT, our number falls nicely between 5.8 and 6.7. So this point must exist at least once. The graph has to touch y value of 6 at least once between 5/2 and 4. So now now that we can guarantee that point, now we're going to look for that point. We know it's a y value of 6. We just have to now figure out pinpoint the exact location and find the x value. So the way we do that is we're going to plug 6 in for the y portion, the y location of our function, and then we can cross multiply, solve for x, and we can factor. And when we factor, we get x minus 3, x minus 2, and that gives us a c value of 2 and 3. So we have 2 locations where this graph is going to reach a y value of 6. But again, we only care about our interval. So we only care about a solution that falls in the interval. So it looks like 2 is outside the interval. Only 3 falls between 2.5 and 4. So we keep 3. So our C value is 3. The only order pair that we care about for that point is 3, 6. But it's just asking for the C value. We already determined what the Y value was. All right, any questions? I want to give a visual representation of this problem in case you are still struggling with how these numbers are related to one another. So what we do is we start off with 5/2 to 4. Here's our function. Our function is a kind of a parabola looking graph, but there's a vertical asymptote at 1, and that vertical asymptote is safely outside our interval. So 5/2 and 4 is nicely protected. We know there's no issues there. And now the next step was to plug in our endpoints. We plugged 5/2 into the function. We got 5.8. We plugged in 4 into the function to get the location of the other endpoint, which is 6.7. So between 5.8 and 6.7, the graph has to cross through a y value of 6. So that was the guarantee there. And now the next thing was to look for the order pair. So we set 6 equal to the function to find the location of the x values. And when we do that, we factor, we solve for x, we solve for c, we get 2 and 3. But 2 does not fall between 5/2 and 4, so that is out. We only keep the one that's between, which is 3. So anytime we see 2 solutions, true, those are 2 solutions that has a y value of 6, but we always have to go back to our interval and only keep the solution that we find in that interval. Any questions? There are additional continuity practice problems that I didn't get to dealing with piecewise functions. So I do want to get to these, but we'll do that on one of the review days. If not Monday, then Tuesday. So we'll come back to it. But I do want to make sure we cover the new materials first, and then we'll come back to the review. Okay, let's go to our notes. Let's see. Okay, infinite limits. This is a limit where the function increase or decrease without bound towards infinity as x approaches c. We know that when we see vertical asymptotes in the problem, we know that the limit doesn't exist. But we're going to try to do this without the use of a graph. And the way that we look for vertical asymptotes is we always pay attention to the denominator of our function. Okay. And as long as that factor in the denominator does not cancel, then we know that we're dealing with a vertical asymptote. So let's just do a little bit of review here. Being able to identify vertical asymptotes versus holes, and being able to tell the difference between when we're looking at a hole and when we're looking at a vertical asymptote. So here I can just factor, right? I'm going to look to see if I can see my individual parts a little bit more clearly. So numerator, multiply, I can factor numerator and denominator. Multiply to be 2, adds it to be -3. Difference of squares in the denominator. Right? It's the factor that doesn't cancel out. That's going to be where our vertical asymptote is. But just as a related piece of information, we know that the factor in the denominator that doesn't cancel out, right? This is still a discontinuity, but that's going to be a hole. Okay, not what the problem is looking for, but I just want to make sure we identify and see the distinction between hole and asymptotes. All right, so now what we're going to do is, for example 2, we're going to have a method. I'm going to refer to these steps as we go through it. We're going to have a method to be able to find what is happening around these asymptotes. Right, around these asymptotes, does the graph look like this? Are the arrows both going up? Are they both going down? Is one going up, going down, or is it vice versa, right? Maybe we know all these our limit doesn't exist, but we want to just be able to get some additional behavior of those of the graph around those asymptotes. And our goal is to be able to, can we do this without having to look at a graph? So let's try that with example 2. Determine the limit as x approaches 2 of our function. So anytime we are asked to find the limit, what is our first step? We always do what first? We don't assume anything, right? We always want to do what first?
Plug in the numbers.
Direct substitution, right? This is an important step because when you plug in, you're going to instantly have an idea how to move what your second step is. Right now, if you don't have the graph in front of you, we don't want to just assume that, okay, there's a hole or there's a vertical asymptote or it's continuous. Let's just plug in, right? If you plug in every time, we're always going to clearly know what is happening at that point. Right? So we plug 2 in. And we get 3 over 0. So what's happening there? Visually, what's happening when we see that result?
It's a vertical asymptote.
Right? And right from the get-go, we can say the limit is what? What's the limit for any vertical asymptote?
Does not exist.
Does not exist. So here, we already have the answer. We already know the limit doesn't exist. Okay, so I want us to make sure we understand that. That's the big picture. We have the big picture taken care of. But what our goal today is, we want to gather information. We want to be able to decide, can we subcategorize beyond limit doesn't exist? Okay, we want to know the behavior of the arrows around the asymptote. That is what we're after. Okay. So what we want to do is, so right now we already know kind of how the graph is looking, right? We have a general idea. Okay. We just want to know, how is the arrow behaving, right? Is it going up? Is it going down? How about the other side as well? So we're going to find the one-sided limit on either side of 2. Okay, so this is how we're going to do it. Just to confirm, we're always going to just make sure that there's a vertical asymptote. So this is also going to extend to the next page, where if this was a standalone problem, we're always going to plug in the x value first, the whole number first, just to get confirmation that we're dealing with something that requires further action. So if I plug 2 in, just like what we expected, we know there's a vertical asymptote. But now we want to know, how is the graph behaving, right? We know that we're approaching a vertical asymptote. So there's only 2 options, right? Either the graph is looking like this, or it's looking like this. Right, those are the only 2 options we're dealing with. So this is nice to know, right? There's only 2 options. We just have to figure out how to choose between these 2 options. So the way we do that is, we want to pick a point that is relatively close to 2 on the correct side of 2. And then from there, we're going to use that to help us determine whether the arrow is going up or going down. So a way that we can do that is, we're going to choose a decimal value that is, in this case, to the left of our argument. But we want to choose a number that is close enough where we're able to get a conclusive read of the behavior. Remember, we're doing this without a graph, so we have to rely on these numbers to help us out. So I want to choose a decimal that is close, within 0.1 to the left of 2.1, right? Right. Whenever we do one-side limit or limit, we always start on either side of our target and then move towards our target. So we're going to test using 1.9 because 1.9 is a decimal value that is within a tenth of our target. That's close. So now we're going to plug 1.9 into the expression, but the whole purpose is to gather whether it's positive or negative. If we get a positive numeric result, we know our graph's going to look like this. It's going to approach positive infinity. If we get a negative value, we know our graph is going to head towards this direction. So I'm going to plug in 1.9 here. So when I plug in our value here, we don't care about the decimal numbers, okay? We just, I mean, the decimal results. We just want to know whether it's positive or negative. 1.9 plus 1, that's a positive number. 1.9 minus 2 is a negative number. If I have a fraction where I have a positive over a negative number, I'm always getting a negative result. So that helps me conclude that my graph is going to look more like this than this, at least from the left side of 2. So we're gathering these information numerically because we don't have the graph. We're kind of creating the graph out of this information. Okay. All right, let's see what's happening from the other side of the asymptote. Again, if I plug 2 in, I'm confirming that it's a 3/0. It's a vertical asymptote. So there's only 2 options, right? If I'm approaching a vertical asymptote from the right side of 2, it's either going to go up or it's going to go down. And the way that we can do that is we pick a point close to 2, but from the right side of 2. So now I'm going to pick a decimal to the right of 2 within 0.1, so 2.1. So numerator, I get positive. Denominator, I get positive. So positive over positive is positive infinity. I know my graph is going to look more like this. So we're able to do a rough sketch of the graph just by using these decimals to help us out. Limit doesn't exist. The arrows are not pointing in the same direction. We can't subcategorize. We'll still say the limit doesn't exist. Just that we can't say parentheses infinity or parentheses negative infinity. Okay. Any questions so far? I want to point out a couple of things that students have asked in the past. They've asked, well, I'm coming from the left side of 2, so why can't I choose an easier number? Why can't I choose 1? Or here, I'm coming from the right side of 2, so why can't I just choose 3, right? Wouldn't that be easier if I just chose 3 and 1 instead of these decimals? And the answer is you could, okay? You could use 1, you could use 3, but you also run the risk of maybe not being close enough to that asymptote and not getting a good read of the graph if you're too far away. So things may change between 1 and 2 that we're not aware of because we don't see the graph. And so we could potentially run the risk of not getting the right sign because we're too far away. So my suggestion is if you use a decimal, you can be safe. You don't have to worry about, getting a false read. And it's relatively easy, right? It looks messy because you're dealing with decimals, but we only care about the sign. So you don't have to know what the decimal numeric value is. Just gather positive and negatives, and then from there, that should be enough to help you because you're only deciding between two options, right?
I have a question, and I think it might just be because I missed something.
Okay.
But how don't we know that the limit doesn't exist once we find the vertical asymptote? Like, I'm not really understanding why we have to make the graph.
Got it.
If that makes sense.
Yes, it does. Okay, let me show you what we're after here. You're right. All the varieties of asymptotes are all limit doesn't exist, right? Those are all limit doesn't exist. But our goal is, can we subcategorize these limit doesn't exist? And unless we know the direction of the arrows, we're not going to know whether it's positive infinity, negative infinity, or no subcategory.
Oh, okay.
Yeah.
So it's just for the subcategories.
Right. Good. It's just for the subcategory. Our big answer is already figured out. We know the big answer is doesn't exist. Now we're just kind of digging into a little bit more detail about the graph. And that's where the decimals come into play.
All right. Thank you.
Good. Okay. Any other questions? I've talked about these one-side limit as subcategories, okay? But then from here on out, you may see the one-side limit as a standalone problem. So if it's a standalone problem and it's a vertical asymptote, then it's asking for just the behavior from the left or from the right side of the asymptote. And if that's the case, then we're just going to look at the behavior of the left side or just from the right side. So even though the full limit doesn't exist, if you just see this problem, a standalone problem, you would give your answer as negative infinity, because this is not asking for the full limit. This is just asking for the movement of the graph from the left side of 2 towards that asymptote. Okay. And then here's the other big idea, the big thing to be aware of. The big thing to be aware of is that for standalone problems, just because you see a one-side limit doesn't mean that it's always a vertical asymptote. Okay? And the reason why that's important is because I could have a one-sided limit for a continuous function, or I could have a one-sided limit for a graph with a hole in it. In these two instances, one-sided limit and the full limit are all consistently the same. There's no distinction between any of the limits if we're dealing with a continuous function or function with a hole, right? Because the limit is the same as from the left, from the right, left, right. They're all the same. So so the reason why I'm stressing that is because sometimes the one-sided limit problems are a distraction. It doesn't have any impact on our problem. We can basically ignore the one-sided limit and we'll just arrive at the same answer anyways. The only time the one-sided limit is going to give you a different procedure is if you confirm that it's a vertical asymptote. If it's a vertical asymptote, then we use decimals because the decimals are going to tell us the locate or the movement towards that asymptote. But sometimes you're going to see limit, one-sided limit, where it's just continuous or a whole. And if that's the case, we don't want to do anything with decimals. So then the question is, how do we know what we're dealing with if we don't see the graph, right? How do we know whether to ignore the one-sided limit or to work with decimals if we don't have the graph in front of us? And the answer to that question is we always have to plug in that argument first. If we plug in that argument, if we plug in that whole number first, that's going to help us categorize between the options that we're dealing with. Okay. If we plug in, if we get a real number, then there's no need to look at decimals. If we plug in, if we get 0 over 0, no need to look at decimals because the one-sided limit is going to be the same as the limit. Now, if you plug in your real number, your whole number, and you get a 5 over 0, 3 over 0, 6 over 0, and there's a one-sided limit, then you're dealing with decimals because now we're trying to subcategorize what's happening on either side of the asymptote. Okay, so I think that's the biggest struggle with students with this unit is students see the one-sided limit and it's just like, well, what do I do? I think students tend to freeze up and just not know. They feel like they got to do something different because there's a one-sided limit. Okay, so we just want to pretend like it's not there and plug in that whole number. And when we plug in that whole number, we can categorize. And if we categorize it, we'll know whether to ignore the one-sided limit or that we need to do something with that one-sided limit. All right, so here is a mixture of different types of problems. And I put a bunch of one-sided limit because I want us to be comfortable with working through the process and not getting distracted by them. So here are the steps. The first thing we do is we always plug in that x value. Okay, we ignore the one-sided limit. The reason why we ignore it is because we have to know what category we're dealing with before we play with decimals. So if I plug in the x value and if I get a real number, then that's it, right? It's a continuous function. Any continuous function, I'm going to get the same read whether I'm coming from the left or from the right. It's just the limit. If I get a 0 over 0, I know there's a hole in the graph, but if there's a hole in the graph, the limit still exists. So it doesn't matter if I'm approaching from the left or from the right, it's the same thing as a limit. The one-sided limit is the same as the regular limit. So we don't have to do anything. We don't have to worry about the one-sided limit giving us a different answer than the full limit. But if we get undefined, if we get 10 over 0, 6 over 0, 8 over 0, then we know it's a vertical asymptote. And if we deal with vertical asymptote and we still see that one-sided limit, then we got to play with decimals because we want to decide between how the graph is, how the arrows are behaving around that asymptote. Okay, let's see how many of these questions we can get through. Let's try number 3 first. Okay. What's our first step for number 3?
Plug in -3.
Right, just -3, right? We don't know what we're dealing with, right? We don't know what we're dealing with. So when we plug in that -3, we're gathering information about the graph. Nine minus 9 is 0. -3 minus 4 is -7. So how do we interpret that result? What does that mean? Is that undefined? Is that a whole? Is that a real number?
The limit is 0.
Good. That's a real number, right? That's a real number. The limit is 0. And if the limit is 0, then it doesn't matter if I'm coming from the left or from the right. It's all going to be the same. Maybe the graph looks something like this. Right? It's a continuous function, so I could be coming from this side. I could be coming from the other side. It doesn't matter. It's all the same answer. So we don't have to worry about the one-side limit because it's the same answer as the real limit. Okay, number 4. First things first. Plug in 0, ignore the one-sided limit. Okay, what do we get?
Zero over 0.
Right. That's important, right? It's important that we plug in that 0 first because this is giving us a lot of information, right? What does this tell us? What's happening at 0 for this graph? There's a what there?
There's a hole.
Hole. Is a limit going to exist? Right. Limit exists.
It could, yeah.
Actually, you know what? For the problems that I give you, if you see 0 over 0, your limit will always exist. Okay, maybe there are some options where 0 over 0 may not lead to limit exist, but the problems that we are dealing with in this course, if you see 0 over 0, you know there's a real number at the end of the process. Right? So we got to eliminate that hole, right? So go back to our factoring steps. So if there's a hole, if limit exists, this one-sided limit is just a distraction. It doesn't mean anything because it's the same thing as a limit, right? We know that once the factors can be removed, we're now free to reevaluate. Again, no decimals, right? We don't deal with decimals unless there is a vertical asymptote at that location. So for these two problems, there's just distractions. One-side limit is the same thing as a limit. We don't do anything different with those one-side limits. Right. All right, number 5. First things first, plug in the -2. Right. Now what do we get?
Five over 0.
Which means that there's what's happening there. What's happening at -2?
The limit does not exist.
Vertical asymptote, limit does not exist. We know the graph looks something like this. We can kind of sketch it out if you like. The full limit doesn't exist, but we look back and we see, okay, it's asking us for just the subcategory from the left side of -2. Right? So now we deal with decimals. We only play with decimals if we realize that there's a vertical asymptote and I'm choosing between two options, either positive or negative infinity. So we can do a test value. A number to the left of -2 is -2.1. And then we plug in -2.1. We get a positive over a negative, which is negative. So we know that our graph looks something like this. And it's just asking for the behavior from the left side. So we don't say it doesn't exist. We say negative infinity because it's just asking for the information from this branch. Yes, the full limit doesn't exist, but this is just asking for the movement from the left side. Okay, I'm over time, so if you guys get a chance, you can feel free to work through the rest of this just for extra practice, but I'll see you guys on Monday. Have a great weekend.
Thank you, Mr. Yang.
Thank you. Have a great
Thank
weekend.
you.
Thank you.
Thanks,
Thank
much.
you.
Thank
Bye.
you.
Thanks, Mr. Yang. Bye.
Enjoy your weekend.
Bye, Mr. Yang. Thank
Bye. See you.
Thank you.
Bye, Creed.
Mr. Yang, I have a question.
Yeah.
So at the very beginning of class, it was like the first minute. My Surface wasn't working, so I joined like a minute and a half late. You said something about finish something by tonight or
Yeah,
over the
yeah.
weekend.
So
is that the diagnostic?
right. If you didn't finish the diagnostic, you finish by tonight if possible.
Okay. I already finished. I'm just making sure.
Okay, you're good then. You're good. Okay.
Okay. Thank you so much.
Thank
Have a nice weekend.
Bye. Have a good weekend.
I have a question too.
Yeah.
So whenever we're solving for these limits and it turns out to be like a vertical asymptote, like and does not exist,
Yeah.
do we always like solve for the behavior?
That's a good question. You see how number 6, it doesn't have a one-sided limit.
Yeah.
So I would say if it's just asking for the full limit, you can just say the limit doesn't exist. I'm not going to ask. Yeah, so technically we could subcategorize by testing both of the one-sided limit, but I would just say I'm not going to ask you to subcategorize if it's just asking for a full limit.
Oh, okay.
Yeah.
Thank you.
Have a good weekend. Bye.